without writing, and I'll do it by voice. Anyway, I'm Guglielmo from Imperial College London. These slides are based on the work by Spencer, who's the NEKTAR project lead, as you saw from the slides by Mohsin. And today I'm just going to be giving you an overview of the flow solvers, the use of the flow solvers when you want to use them, what sort of practical implications there are, the incompressible solver, then the discretization scheme mainly in time. So how do you advance in time using the velocity correction scheme, or the logic how would we get there? The compressible solver mainly according to the discontinuous Galerkin formulation, and then of course things like preconditioning I will touch upon, and then finally aliasing and stabilization, which are of course more of an art at this point rather than a true solution. So let's start off with low speed flows or low compressibility flows. You're in the incompressible range. So now the Mach number is beneath 0.3, or density variation beneath 5%. And this is of particular interest to the external aerodynamics of the automotive industry. And on the left, you can appreciate the complexity of the geometry. But one of the main things I want to bring your attention to are the different length scales that appear in the configuration. And you can see that you've got your large scales, that contain the largest kind of energy, and then of course the smaller ones, which are more difficult to deal with because you're going to have to resolve them, because otherwise energy accumulates in your solution and diverges, because we're not yet at the point where we can resolve everything in quasi DNS range, or DNS range if you prefer. And therefore energy tends to build up in the small scales and cause divergence. There are practical cases where you would go for incompressible solvers, even though it doesn't really make sense out of sort of common sense. And this is a compressor on the bottom right-hand side. And the reason why I went for that particular solver is because the experimental data was in incompressible range. And this allows me not only a saving in terms of number of PDEs I'm solving, so you go from your 5 PDEs to 4 in incompressible range, but because this particular configuration is a 2D configuration extruded in the spanwise direction with periodic boundaries, I can also use a Fourier expansion, which adds further savings. So there's always this kind of gauging what is the cost and what are the flow conditions and what sort of resources I have. And then there are cases where I can't do anything else other than utilize the compressible flow solver and have significant resolution to try and capture the flow physics correctly. And as you can see on the top left-hand side, an intake with shocks forming with reflections, of course, and then on the bottom left-hand side, a high-pressure turbine, which has been my work over the past 3 years. And you can see in the sort of grayscale image at the back, the pressure waves forming in between blades, traveling from the trailing edge of one blade to the suction side of the neighboring one. And then, of course, as you rank up the acceleration, how do you do that? Well, you just reduce the back pressure. A shock forms at the trailing edge, and you see that on the right-hand side. And just to give you an idea, this particular flow condition goes from an incompressible kind of setting at the inflow of Mach number 0.15, so you're well within the incompressible range, to 0.8 to 1.1 within 10 centimeters. So it is a rather expensive case to do. So moving on to the incompressible solver. So I'll sort of, well, it's always nice to see the Navier-Stokes equations in all their glory. And then, of course, trying to relate these to the explicit time step to why we go for a correct velocity correction scheme. And then finally, the need for a pressure boundary condition to make the problem well posed. So here are the Navier-Stokes equations in incompressible format, and you will note that because the first term on the left-hand side is only got the velocity terms and the numerator. You've got your convective terms, which are nonlinear in yellow, and then your pressure terms on the right-hand side, and your viscous terms at the end in pink. Now, in shorthand notation, of course, you've got U represented as a vector of UVW if it's 3D, or in 2D of UV in this case. But the main point is that the divergence is going to be 0. This is the characteristic of incompressible flows, which makes things like inflow turbulence kind of techniques rather complicated. Anyway, highlighting the yellow terms, the convective nonlinear terms, and the linear diffusive terms on the right-hand side, we come to time step restriction. So in the linear world of finite difference or finite volume, your time step restriction is mainly dictated by the velocity v. So your time step is inversely proportional to how fast your flow travels. There is, of course, a dependency on your mesh spacing, and of course, as much as you start reducing your spacing, you're going to start resolving more and more, and therefore it's going to play an effect on your time step. The diffusion term, on the other hand, is only inversely proportional to the viscosity or the diffusion coefficient sigma at the denominator. When you move into high order kind of configurations, your spatial delta x is not the linear one anymore. Okay, you can use the same mesh and you will have the same delta x, but now your spacing is delta x over p squared, which you can plug into the stability conditions determining your time steps. And as you can see, for the nonlinear convective terms on the top, you get a scaling of p squared. So now if you go to P4, you're going to get 16 times the scaling of the time step, and the diffusion terms at the bottom will go to 16 times scaling of the time step only for P2. So the diffusion terms can be handled with an implicit discretization, while the advection terms, being nonlinear, are more complicated to handle in terms of a implicit discretization. So we stick to an explicit one. We therefore come up with this IMEC scheme, which is short for implicit, explicit, and this is how it works. It's the velocity correction scheme. So you've got at the top the shorthand version of your Navier-Stokes equations there, where the main sort of point of interest is the capital N in bold font there, which represents the full nonlinear terms. And then, of course, you've got your divergence condition, which plays an important part. On the right-hand side, you've got how the every time step works. So you first deal with your nonlinear terms in an explicit fashion, and then you move on to, you determine this sort of intermediate flow field state of the velocity vector, and then you plug this into the pressure equation and the Helmholtz problem and solve an implicit kind of time-wise discretization, and then you move on to the next time step. Okay, so you have this intermediate U plus there, which is just a combination of the current state of the velocity and the nonlinear terms determined by the previous velocity states. You then have a Poisson equation and a Helmholtz problem at the end. And the Helmholtz problem, you note that the exponent, which is not to the power of, but rather the current time step, or the next one. So n is the current time step, and n plus 1 is the next one, and minus 1, of course, by default is the previous one, ensures that we are solving an implicit problem. So where does it all come from? So let's start with the first term. So you have your unsteady velocity vector. You want to determine the derivative at the next time step. So what you do, Taylor expansion and or finite difference, if you want to be more precise, and depending on your coefficient alpha naught and of course how many previous terms you store. So of course you don't want to store too many because then you just run out of memory. But in this case, if you want a second order discretization, you would store the current one and the previous one in order to recover second order accuracy of the derivative. You then finalize your backward difference formula for that particular term, and then you use an extrapolation for the nonlinear term. Of course, you don't have the velocity field at the next step. So what you use is the current step, and then, of course, you extrapolate backwards. And the further back you go to determine the nonlinear terms, the greater the accuracy. Of note is that the coefficients are always 1 of these particular terms, and if you add them up, so even when j is 2 in the second row here, hopefully you see my mouse, you still get 2 minus 1 is 1. Why is that? Well, because if the solution is steady, so you can imagine you're running an aerofoil, a NACA 0012, with a far field, and very distant from the far field, you're going to get very minute, almost non-existent differences, and your solution is steady. So you want to maintain that steadiness there. That's why the coefficients always add on to 1. You then move on to, so we've moved on to discretizing the left-hand side. We're now missing the right-hand side of the implicit time step. So how do we go about that? So we've got the splitting in time discretization. As I mentioned, you split things, you go step by step. So what happens is you have your U plus from the nonlinear terms on the previous unsteady time term. You then determine your U plus, which is this intermediate step, and you plug it into the unsteady term with the pressure gradient equation. Now, you end up with the Laplacian of the pressure plus equals to the divergence of the velocity this intermediate velocity you have obtained from your previous time step. Okay, so this means that we've gotten rid of U hat plus. If you see it here, there is no U hat plus, and therefore the this equation results here. You therefore you can get your pressure distribution, and therefore we can at the next time step, and therefore we can solve the Helmholtz problem too. So you've got everything at time step n+1. Once again, these are not exponents. They are, well, sorry, to the power of, they are exponents. They indicate the next time step, okay? Where you also have the U plus here, which indicates your intermediate solution coming from the first step involving only the left-hand side of the original Navier-Stokes equations in incompressible form. So how did we get rid of the U hat plus, this further intermediate step? Well, we simply assume that we know from the incompressible Navier-Stokes equations that the divergence of the velocity has to be 0. So we can say that the divergence of U hat plus is also 0, assuming that it is equal to the exact solution at UN plus 1. Of course, it's not. It carries a certain degree of error. And as you can see at the bottom, this is called splitting error. What happens is this is proportional to the time step squared. So the smaller the time step, which in any case is governed by the explicit part of the splitting scheme, so the convective terms. So because it's explicit, it's still going to drive down the time step and limit you. So as a rule of thumb, it's generally okay. And then, of course, as you refine your time step more and more, you're going to get less and less errors. But nonetheless, it's worked very, very well for us. So I mentioned I was going to talk about the pressure equation in a little bit more detail because we need boundary conditions for it to have a well-posed problem. So where do these come from? So taking a more sort of mechanical approach, and then I will sort of discuss it very briefly in the next slide. What happens is your momentum equations are a set of vector equations. So you've got, if it's in 3D, you've got your momentum in U, your momentum in V, and your momentum in W. So you can dot product them with the normal to the surface because you're at the boundary, right? And then rearrange it such that your pressure gradient is on the left-hand side and all the other terms are on the right-hand side. So on the right-hand side, you end up with the viscous terms at the next time step, the unsteady term, and the nonlinear term. The nonlinear term, of course, is going to be evaluated utilizing the backwards extrapolation as indicated by the n star at n+1. But for what concerns the Laplacian of U, we would like to enforce divergence. Now, using a vector calculus identity, you can write the Laplacian of the velocity vector as the gradient of the divergence minus the double curl, if you will, of the velocity vector. If we set the velocity divergence to 0, we end up with the Laplacian of U being equal to minus the double curl of the velocity. Okay, so this results in the equation at the bottom, where I now have my pressure the gradient quantity at the next time step as a boundary condition equal to a set of parameters on the right-hand side. of note is that you normally, this is a von Neumann boundary condition, and that, for example, at walls you will be setting it to 0, or at exits you can set it to 0. So this will be enforcing all the right-hand side you see there. So where does it all come from? So mathematicians Wermon and Shen actually showed how you can derive this particular formulation, and this is the part where I would have liked to have been able to write, but never mind. Try and do it by voice only. So what happens? You've got your equation at the top, which is the shorthand version of the Navier-Stokes equations in incompressible format with the n+1 exponent, and that is because it is implicit. And you can reduce this to utilizing the method of weighted residuals, which Mohsin has outlined earlier on, to the one below, which is just the gradient of the basis function multiplying each and every term of the incompressible Navier-Stokes equations. So this so that's a shorthand version. So each and every one of those is just the integration over the domain of the gradient of the basis function dot producted with each and every one term. So to further sort of see how we end up with these boundary conditions that are required for the pressure equation, we just apply the divergence term and we rearrange, and we end up with what you see at the bottom, which is basically your basis function integrated over the domain and multiplied by the gradient of your, well, the divergence, excuse me, of your unsteady term, of your nonlinear term, and then of your pressure gradient. And then, of course, you recover once again the divergence, in this case, of the double curl of your velocity vector minus a boundary condition term. Okay, so this kind of tries to put the overall Navier-Stokes discretization using the velocity correction scheme with a pressure equation that requires boundary conditions to be able to be solved. And this is the overall system of equations. So if you take your weak formulation of the incompressible Navier-Stokes equation, this is identical to solving the problem below, where you also, apart from pressure equation, you also have the boundary condition and therefore a well-posed problem. And then you just go ahead and solve your system of equations at the bottom. So you got, well, these two are inverted order. So you've got your velocity, intermediate velocity from previous time steps, and your pressure equation, and then your pressure boundary condition, or von Neumann boundary condition. Okay, so one thing I wanted to bring your attention to, and I mentioned earlier on, was the Fourier expansion utilized in homogeneous domains. So an homogeneous domain is simply a 2D domain that is extruded in a homogeneous fashion in the Z direction. You can put symmetric boundary conditions if you want at the end, but you normally end up putting periodic ones. With periodic ones, you can use a Fourier expansion that allows you to solve it in roughly half the amount of time, or half the amount of resources, in very roughly, with respect to a physical extrusion. Why can we do that? Well, because the velocity correction scheme has an implicit term which is linear, the one highlighted in orange, but in blue you've got your nonlinear terms which are explicit, and this allows you to solve the solution as a series of Fourier planes. Each has got two Fourier modes, and therefore, of course, cut your overall runtime, and you don't even have to store the 3D mesh, because you just have to give it a 2D mesh, and then it transfers information through it with the Fourier expansion. Okay, so I thought this was it's generally a useful tool to know, because a lot of the times in academia you end up running relatively simple geometries due to computational costs or lack of resources. So so in the incompressible solver, I've showcased sort of the time step, how you get to the velocity correction scheme, and then again how you get the pressure boundary conditions, and I've given you this neat trick of the Fourier expansion. For the compressible solver, I'm going to move on to the discontinuous Galerkin formulation. Now, previously we had the continuous Galerkin formulation, which Mohsin spoke about, where your basis functions are continuous across elements. So at the boundaries, your primitive variables, so your U, V, W, and P for your incompressible solution, are the same between neighboring elements. For the compressible flow solver, you tend to prefer this continuous Galerkin formulation because of the presence of, for example, stuff like shocks. So at this point, you're going to end up with fluxes in between elements. So you've got an elemental composition rather than having the whole matrix in front of the system representing the overall domain, and therefore have to understand how to transfer information in between elements. So the state, how does the state of one element influence the neighboring state and vice versa, so that your solution can evolve. So you start off, for example, with the simplified equation at the top, where you've got your method of weighted residuals, but this time it's applied to each and every element. So your summation over E is over every single element. In this case, on the left-hand side, you've got 4 of them. So you're going to be summing from 1 to 4. And you've got your weak formulation, which is your basis function times du dt plus the divergence of f of u is equal to 0. Now, by applying integration by parts and then the divergence theorem, we then are able to recover the formulation you see in the middle, where now you've got you still got the summation over all elements in the domain, but now you've also got a term which is on the boundaries, which is indicated by the pointy brackets there and is integrated over the surface. Because if you remember, the divergence theorem will take a the divergence of a quantity is integrated all inside a control volume if you're a finite volume person, or inside an element if you're a finite element person, or general volume, and will equate it to the dot product of that quantity times the normal to the surface and integrate it over the surface. So we've managed to crucially recover a term which is called f hat of u, which is an upwind flux, and I will explain what I mean by upwind from our equation. We then integrate by parts again, and we end up with the third line you see there, which is now once again a summation over all elements, but of the original equation. And crucially, you've added in a flux quantity and the quantity evaluated over the entire element inside, once again, the pointy brackets. So we've gone from the original equation, and we've utilizing simply integration by parts and the divergence theorem twice, we've managed to recover the original equation plus the information we need to transfer the data from the state of one element to another one. Okay, so we then need to determine, I mentioned upwinding, so we need to determine the state at the interface and solve our Riemann problem, which can be solved with, for example, a row scheme. For those of you who have done finite volume more extensively. So how do we determine? We need to determine the information that is propagated to that interface, and this is determined by upwinding. So you take the information from where it comes from. So if your velocity, which is determined by taking the chain rule of the divergence of your f of u, which is simply ends up being df, du, dx, will give you the sign of the velocity. So if it's pointing, for example, if the velocity is going towards your left, you will get information from your right. And if it's pointing to the right, you will take information from the left. Basically, put very simply, what happens downstream is affected by what happens upstream. Okay, that is both true in time and in space. So this is the discretization of the convective terms. So we move on to the diffusive terms. Now, the problem with the diffusive terms is that you can't really determine a quantity at an interface using directionality, because diffusion just propagates everything. You think about how temperature, for example, diffuses, or viscosity, how it diffuses. So there's no real directionality information. So how do we deal with this? So consider the scalar diffusion, the scalar steady diffusion equation, as you see at the top, and you end up with your Laplacian of u is equal to a quantity f. Now, we introduce an intermediate auxiliary variable, so we just set our q vector equal to the gradient of u, and then the dot product of nabla with q is equal to f. So now you've got two equations. You convert them to the elemental integral form, as you see at the bottom there. Yeah. Sorry, someone had a question, or? Okay.
Oh, sorry, just echo. Just go ahead.
Okay, thank you. What happens is you now end up with two sets of equations where you're going to take the weak formulation. So your curved brackets indicate the weak formulation. So you've got your psi times q is equal to psi times nabla of u, and then of course psi times the divergence of q is equal to psi times f. Okay, so this is the only trickery we've done to avoid second order derivatives, mainly because then the second order derivatives you take the two derivatives of a linear basis function and you end up with zero. So you can't do much with that. So we've got this formulation you see here at the top, the elemental integral form. And now what do? We apply the same trickery. So we've got the integration by parts applied only once to the two sets of equations, and highlighted in green are the terms that you need to evaluate on the interface, right? So that you can carry out your integration. So how do you deal with diffusion that doesn't have any real directionality? You could take the left one, you could take the right one. There's two schemes that are highlighted here. So the first one, BR, stands for Bassian-Rebaille, and is the most obvious idea. So you just average the quantities on the two sides of the interface, right? So you take U3 plus U4 and you average it, and Q3 and Q4 and you average it. The linear discontinuous Galerkin formulation simply uses a blend. So you utilize at the interface, you utilize U3 and Q4, or vice versa, Q3 and U4. So you kind of mix the two. Okay, so we've gone through the discontinuous Galerkin idea. I mentioned to you that we don't apply the continuous version as we do in the incompressible version, so we don't end up with this massive mass matrix at the in front of the entire system that needs to be solved for the whole domain. We now have elemental kind of matrices that need inverting and are much easier, and we just transfer information from one element to another. In the advection case, utilizing the upwinding philosophy, whilst in the case of the viscous terms, we can use a little bit more imagination and use either an average, or as in this case, we mix variables. Okay. So I mentioned the spatial discretization a little bit. So let's talk about the why we go directly to implicit for the discontinuous Galerkin incompressible solver. Well, I brought up this slide once again just to remind you that your time step for the high order discretization will scale inversely to the polynomial order, and becomes particularly difficult for the diffusion. But in this case, it also makes sense given that we're not using a large mass matrix for the entire domain where we've got local ones. We can also consider an implicit scheme for the convective terms. So how does it work? Well, we start off discretizing your Navier-Stokes equations at the top. So you've got your compressible flow equations in steady term, your inviscid fluxes equals your viscous fluxes. You spatially discretize it using the method of weighted residuals. So you end up with a local mass matrix. Multiplying your unsteady term is equal to your discretized inviscid fluxes plus your viscous fluxes. and then you carry out an implicit time discretization where you've got your next time step depending on your previous time step. And of course, because it's implicit, you've got your u of n plus 1s appearing on both sides of the equation. You finally end up with a linear system, which you can see at the bottom, which you solve using Newton methods. So basically, you go along the line you see on the right-hand side. Is this okay? On the right-hand side, which is non-linear because otherwise it would be a straight line. You take your initial guess, u0, which can come from the previous time step, determine the slope, which you see in red. You go all the way to the x-axis, determine your u value there, project it onto the curve, take another gradient, and you move to u2, and so on and so forth until you reach convergence, or generally based on user-defined quantities. Now, because this is a Taylor series expansion, we then end up with a linear problem, which is ax is equal to b, and this we can solve with a GMRS kind of type of scheme, where the perturbed nonlinear terms, or the Jacobian matrix, so partial n, partial u, can be done through a Taylor series expansion where we just perturb the nonlinear terms by a very tiny amount epsilon, and then determine partial n, partial u times x in a sort of Jacobian free manner, so you can reduce the memory footprint of your scheme. Okay. Before I move on to problems, basically divergence and stabilization, let me just mention preconditioning. You have heard probably of block Jacobi methodologies, or incomplete lower upper factorization, or ILU. So why are these required? Well, you need to invert the Jacobian matrix, and the original formulation of it is going to have the eigenvalues, which you see on the x-axis of the left-hand side plot, are going to be spread over a very wide range. So they're going to go, in this particular case, from 0 to over 100. So to be able to quickly find these quantities, you can use preconditioning, and that of course reduces our range. And you can see that from the 0 to 100 range, we've now gone from 0 to roughly 2 for all possible preconditioners. And well, the ILU seems to be doing better in this particular case, and therefore it's going to be much easier for us to find those roots, those eigenvalues for our particular inversion. Okay, so I've highlighted the compressible flow solve, and we move on to discontinuous Galerkin. We require the transfer of information from one side to the other of both the convective terms. You do it through upwinding, and the diffusive terms, which you do through some mix and match or some averaging, because it doesn't really have a direction. We move on to aliasing and stabilization. So I'm going to try and give you an idea of what goes on. So the Navier-Stokes equations, nonlinear terms, are second order. So you've got, if you imagine at the top, you've got two sinusoids. So what happens is you're going to generate a harmonic with double the frequency. So you don't know what this is, and you're going to go and mesh your domain, as you see on the bottom left-hand side, and you're going to try and guess what is going on. Otherwise, you wouldn't do it. You just know the solution to start with. And these waves form and can cause divergence, particularly in regions where you think things are going to diffuse out, or you're not interested in, because you remember, with these kind of simulations, you're always trying to hack the system, if you will, in a very poor sort of terminology, and try to save resources and get your solution out as soon as possible, right? So what happens in another case is, if you have a mesh expansion, as on the bottom, you see this 1D mesh, where on the left you've got a fine set of elements, and then you've got on the right a rather aggressive expansion. Third wave trapping.
Yes.
Brilliant. Okay, so aliasing. So on the bottom right-hand side, you see the sinusoid, this high frequency sinusoid forming. This is a 20th order polynomial, and we go and integrate it with a 12th order quadrature, and you can see that whilst it does kind of follow an oscillatory behavior, it is a very poor reconstruction. So if we then go and have a look at the expansion coefficient of the graph, the bar chart at the top, so you've got your expansion coefficient on the left and the expansion mode at the bottom. So because of this under integration, you can see that the deviation in red from the exact value of the expansion coefficient at higher and higher modes starts to increase. This means you're introducing an error, and of course this will gradually accumulate energy and cause explosion of your solution. And of course, the more points you have, the more expensive your solution becomes. So you've got three types of aliasing. You've got PDE nonlinearities. I mentioned those when we spoke about the harmonics forming when you've got your nonlinear terms, your nonlinear convective terms that generate twice, four times, and so on, the harmonics. You can try and treat these by trying to determine how many quadrature points you need in every direction of every element, but this is rather tricky. It helps you reduce the computational cost, but it's not something I would recommend because you're not gonna know a priori. So you then move on to a second type with the geometric deformations or negative elements. So basically in high order formulations, you want to capture the curvature of the geometry because you're using a coarse mesh. So you can capture the CAD exactly. The problem with that is that you're going to end up coarsening the mesh too much sometimes. And this is going to just create negative Jacobians. So you remember when Mosen explained the mapping from the physical domain to the elemental domain and backwards, you needed to determine a Jacobian. If you've got far-field elements, it's going to be a linear equation, but for the curved surfaces, you now need to introduce this curvature as well. So you can get negative elements and therefore your solver will not run. Then interface aliasing, that's for the discontinuous Galerkin formulations, and this is just due to the reduced number of integration points along the interface to be able to reconstruct your fluxes and diffusive terms. How do you sort these out? So I'm going to concentrate on the incompressible methodologies because I believe that most of the interest is around these. We do have stability methods for the compressible solver, and it's running well, as I showed you with the high pressure turbine case. But nonetheless, I will deal with these because they are also the older versions. So you've got your spectral vanishing viscosity, or SVV. So if you consider the nonlinear Burgers equation, which you see in the equation there, except for the right-hand side, which is the damping criterion, what happens in the bottom image when you plot it, you can see that spikes occur where the high order sort of nature of the solution starts accumulating energy because there is not enough resolution. So what you do is you have a filtering strategy, which is a Q kernel, which tries to determine which frequencies to damp. So you don't want to damp the entire set of frequencies. You just want to damp the higher frequencies and have sort of a cutoff, right? So you can resolve the lower frequencies, which are generally more easily resolved by a coarser mesh. You then have the gradient jump penalization, or GJP. This is a more recent introduction into NEKTAR, and all it is, if you consider a C0 continuity across elements of the continuous Galerkin formulation, what happens is you, apart from having your primitive variables be equal on the two sides, you can try and weakly enforce C1 continuity, so continuity of your gradients across elements, and this helps stabilize it, but also allows you to gain 2 orders of magnitude accuracy with respect to the use of the spectral vanishing viscosity. So to finalize, I have given you a logic behind the two solvers. There is the incompressible one, the compressible one, when you would use them, try and take shortcuts in terms of amount of resources and runtime required. The overall philosophy around the incompressible Navier-Stokes solver, going from the time step, the high order problem, scaling of the time step, the velocity correction scheme, you've got this IMEX formulation, the weak to have a proper problem, you need the pressure boundary conditions. And then finally, you move on to the compressible flow solver, discontinuous Galerkin, upwinding, diffusion needs different treatment, the preconditioning, and then aliasing and stabilization. So you've got 3 types of aliasing and then 2 types of stabilization for your incompressible flow solver. So that is it, which I have sort of fulfilled the